December 26, 1944. Ardennes Forest, Belgium. The Panther tank commander felt invincible behind 80 millimeters of face-hardened steel. Sloped at 55 degrees, his Glacis plate offered protection equivalent to 140 millimeters of vertical armor. The Americans couldn't touch him frontally. Their 76-millimeter guns bounced off like pebbles. Even the British 17-pounder required point-blank range. Then the sky cracked open. The shell never hit the tank. Instead, it detonated 30 feet above the Panther's turret. A perfect airburst that transformed the winter sky into a storm of molten steel fragments. Inside the crew compartment, 5 men heard the hammering begin. Metal rain against their roof. The sound changed, from hammering to tearing. The Panther's frontal armor sat untouched, pristine, exactly as designed. But the thin roof plate, 16 millimeters, designed only to keep out rain and small arms fire, shredded like wet paper. Shrapnel fragments traveling at supersonic velocity punched through, ricocheted inside the cramped fighting compartment, tore through flesh and bone. The screaming lasted 8 seconds, then silence, except for the idling Maybach engine and the hiss of escaping steam. The 45-ton beast that had terrorized Allied tank crews from Kursk to Normandy sat motionless, exterior unmarked, crew dead inside. Killed by a weapon that completely ignored its legendary armor. Across the frozen Belgian countryside, this scene repeated with mathematical precision. American artillery batteries were firing shells equipped with a device the German High Command didn't know existed. A 5-pound electronic marvel containing miniature vacuum tubes, radio transmitters, and circuitry that could survive 20,000 times the force of gravity. Cost per unit, $18 by late 1945. Less than a tank crew's monthly wages. The device had a cover name, Variable Time Fuse, VT for short. Deliberately misleading, suggesting it was just an improved timer. The reality was far more revolutionary. This was the world's first smart weapon, a proximity fuse that used Doppler radar to sense when it was exactly the right distance from a target, then detonated with perfect precision. Against aircraft, it tripled kill rates. Against ships, it quintupled effectiveness. Against tanks, it rendered their armor design philosophy obsolete. The Germans called it Teufelmunition, devil's ammunition. They couldn't understand how shells consistently exploded at optimal height without any visible aiming adjustments. Some theorized magnetic sensors. Others suspected acoustic triggers. A few entertained wild ideas about Allied psychics guiding each shell. The truth was simultaneously simpler and more sophisticated. The Americans had miniaturized radar technology into an artillery fuse. They'd solved manufacturing problems German scientists deemed impossible. And on this frozen December morning, they'd just turned the Panther tank, arguably the finest armored vehicle of World War II, into a death trap. The weapon that ignored Glacis armor completely. The $5 fuse that changed armored warfare forever. Stay with this story. 18 months earlier, Allied intelligence officers faced a strategic nightmare. June 1943. North Africa. British tank crews examined their first captured Panther. The measurements told a grim story. Upper Glacis, 80 millimeters thick, angled at 55 degrees from vertical. Effective thickness against perpendicular impact, 140 millimeters. Lower Glacis, 60 millimeters at 55 degrees. Side armor, 40 to 45 millimeters. Turret front, 100 millimeters of cast steel. American engineers ran penetration calculations obsessively. The standard 75mm M3 gun on Sherman tanks couldn't penetrate the Panther's Glacis at any combat range. 0 meters to 3,000 meters, no penetration. The newer 76mm gun performed marginally better, but still couldn't defeat frontal armor beyond point-blank range. British 17-pounder guns could penetrate at 200 yards. Maybe, if the crew survived long enough to get that close. And if they had the scarce tungsten core ammunition that was perpetually in short supply. The Panther's own gun, the 7.5-centimeter KWK-42L70, could penetrate 139 millimeters of armor at 1,000 meters. It could kill Shermans at ranges exceeding 2 kilometers. The Germans were producing these monsters at MAN, Daimler-Benz, and MNH factories. Production targets: 250 units monthly. Do the mathematics. Each Panther required 3 to 5 Allied tanks to destroy it. Each engagement cost Allied lives. Germany was producing 6,700 Panthers total during the war. Even accounting for mechanical breakdowns, and the Panther had notorious final drive problems. That meant potentially 20,000 Allied tanks destroyed. The strategic implication was terrifying. Allied armor would be bled white before reaching the Rhine. Every mile of advance would cost exponentially more lives as German tank quality improved, while Allied numbers advantage diminished. But buried in those intelligence reports was another number, one that artillery officers noticed immediately: 16 millimeters. The Panther's roof armor measured 16 millimeters thick. Homogeneous steel, not face-hardened like the Glacis, designed to protect against overhead shell fragments and small arms fire. Tank designers had reasonably assumed that artillery shells would either impact the ground or strike thick frontal armor. They never considered proximity fuses. By late 1943, American ordnance planners understood the problem clearly. You couldn't defeat the Panther frontally with available tank guns. Flanking attacks worked but required tactical superiority and crew skill. What if there was another approach entirely? What if you didn't penetrate the glacis at all? What if you simply bypassed the armor from above? The technology already existed. Proximity fuses developed for anti-aircraft warfare. Naval gunners had been using VT fuses since January 1943. The USS Helena's first kill off Guadalcanal proved the concept. But the Pentagon absolutely forbade using proximity fuses over land. The risk of capture and reverse engineering was too great. That policy was about to change, because the Ardennes offensive would force Eisenhower's hand. And the Panther's 16-millimeter roof was about to become its fatal vulnerability. Johns Hopkins University Applied Physics Laboratory, Baltimore, Maryland, 1940. Physicist Merle Tuve stared at the components scattered across his workbench: a radio transmitter, receiver circuitry, 4 miniature vacuum tubes, battery assembly. On paper, the concept was elegant. Build a Doppler radar small enough to fit inside an artillery shell nose. When reflected radio waves detected proximity to a target, trigger detonation at optimal distance. The problem? These delicate components had to survive being fired from a 5-inch naval gun. 20,000 times the force of gravity, for 0.02 seconds. Impossible, said Navy engineers. Vacuum tubes shatter under those forces. Glass breaks, filaments snap, solder joints fail. Tuve's Section T team at Applied Physics Laboratory proved them wrong through methodical obsession. They partnered with Western Electric and Sylvania Electric to redesign hearing aid vacuum tubes for extreme shock resistance. Every component was tested to destruction, analyzed, redesigned, retested. The solutions emerged through trial and error. Planar electrodes replaced fragile wire filaments. Tubes were embedded in wax and oil to equalize stress distribution during firing. Shock hardening techniques borrowed from watchmaking were applied to electronic components. The fuse body itself became the radio antenna, eliminating external protrusions. Setback switches armed the fuse only after experiencing gun acceleration. A small battery with delayed electrolyte activation prevented premature detonation. The shell had to clear the gun barrel before the circuit became live. Safety mechanisms required both linear acceleration and rotational spin from barrel rifling. The oscillator transmitted continuous radio waves at 45 to 90 megahertz. When approaching a reflective surface, aircraft, ship, or ground, the Doppler shift caused frequency changes in reflected signals. An amplifier boosted this difference. When the frequency matched preset parameters corresponding to optimal burst distance, a thyrotron tube closed the detonation circuit. August 12, 1942. Chesapeake Bay. The newly commissioned USS Cleveland aimed her 5-inch guns at 3 radio-controlled drone aircraft. The test protocol called for 2 days of firing to evaluate the new VT fuse under simulated combat conditions. Navy brass watched from observation posts. First salvo. 4 shells fired, 3 drones destroyed. The test was canceled immediately. They'd seen enough. Mass production orders went out that afternoon to Crosley Corporation, RCA, Eastman Kodak, General Electric, and McQuay Norris. By September 1942, the first accepted production fuses rolled off Crosley's assembly lines, 500 units. By late 1943, daily production reached 40,000 fuses. By war's end, 70,000 per day. Total production exceeded 22 million units. Each fuse contained approximately 130 miniaturized electronic components assembled with precision rivaling Swiss watchmaking. Early production cost, $45 per fuse. By 1945, with optimized manufacturing, $18. The entire program cost exceeded $1 billion 1940s dollars, roughly $15 billion in modern currency, but the results justified every penny. A single VT-fused 5-inch shell could accomplish what previously required 1,000 conventional rounds. Against kamikaze attacks in the Pacific, the fuse was credited with saving hundreds of ships and thousands of American lives. Now that same technology was about to revolutionize ground warfare, the question was whether the Pentagon would allow it. January 5, 1943. Waters off Guadalcanal, Solomon Islands. 4 Japanese Aichi D-3A Val dive bombers emerged from cloud cover at dawn. The obsolete aircraft were slow, maximum speed 240 miles per hour, but their dive bombing accuracy made them deadly. One Val scored a direct hit on the New Zealand cruiser Achilles before the formation broke off northward. Lieutenant Red Cochran commanded the aft 5-inch battery aboard USS Helena. His gunners tracked the departing Vals, range increasing rapidly. Under normal circumstances, this was a wasteful engagement. Enemy aircraft fleeing at maximum speed, range exceeding 3,000 yards and opening. Conventional time-fused ammunition would require dozens of rounds for a possible kill. Cochran ordered VT fuses loaded, 3 salvos, 6 shells total. 2 proximity-fused rounds passed within lethal distance of one retreating Val. The fuses detonated without touching the aircraft. Airbursts creating overlapping shrapnel patterns. Fragments shredded the Val's control surfaces, punctured fuel tanks, killed the rear gunner. The dive bomber rolled inverted, trailing smoke and flame, then plunged into the Pacific. First combat kill by proximity fuse. Helena's action report noted the engagement time, approximately 40 seconds from target acquisition to splash. Ammunition expended, 6 rounds. Previous doctrine would have required hundreds of shells for a retreating target at that range and speed. The tactical implications spread through the Pacific Fleet like electricity. Naval commanders who'd previously accepted horrendous casualty rates from Japanese air attacks suddenly had a weapon that tripled their defensive effectiveness. Ships equipped with VT fuses began actively seeking engagement with enemy aircraft. By mid-1943, proximity-fused anti-aircraft fire was credited with more than 50% of all Japanese aircraft shot down by naval gunfire, despite VT fuses comprising only 25% of ammunition expended. The mathematics were unambiguous. Proximity fuses were outperforming conventional ammunition 3-to-1 in actual combat conditions. But this success created a strategic dilemma. The fuse's effectiveness was so dramatic that enemy intelligence would inevitably notice. Japanese and German analysts would study engagement reports, notice the sudden spike in American anti-aircraft lethality, and begin investigating. If they captured an intact VT fuse and reverse-engineered the technology, Allied bomber formations could face devastating losses. The Pentagon's decision was absolute. VT fuses could only be used over water where duds would sink beyond enemy recovery. This policy was classified at the same level as the Manhattan Project. Fewer than 100 people in the Allied command structure knew the fuse's true operating principle. For ground forces in Europe and the Pacific, this meant watching the technology exist but being forbidden to use it. Artillery officers saw Panthers massacre their tanks and begged for anything that could stop German armor. They were told no. The secret was too valuable to risk on land where enemy forces could recover unexploded shells. This policy held firm through 1943 and most of 1944. American soldiers died. Allied tanks burned. The proximity fuse remained locked away, used only where the ocean guaranteed its secrets stayed hidden. Then, December 16, 1944, changed everything. The Ardennes offensive forced a choice between secrecy and survival. December 16, 1944. 0530 hours. Ardennes Forest, Belgium. The stillness shattered. 2,600 German artillery pieces opened fire simultaneously along an 85-mile front. The barrage targeted thinly stretched American positions held by 4 divisions, spread across terrain considered a quiet sector. The surprise was total. 410,000 German troops surged forward through snow and fog. The assault force included approximately 1,400 tanks and assault guns, 400 of them Panthers and Tigers. Supporting them, 1,600 anti-tank guns, 2,600 artillery pieces, over 1,000 combat aircraft of the Luftwaffe. Adolf Hitler's objective was audacious. Split the Allied armies, capture the port of Antwerp, encircle and destroy 4 complete Allied armies, force a negotiated peace in the West, then redirect all forces to stop the Soviet advance from the east. Within 48 hours, German spearheads had penetrated 30 miles into Allied lines. American casualties mounted catastrophically. Entire units were surrounded. The 106th Infantry Division, freshly arrived in Europe, lost 2 complete regiments. Communication lines were severed. Supply routes cut. Panic spread through rear echelons. General Dwight Eisenhower faced the worst crisis of his command. He immediately ordered massive reinforcements. Eventually, 610,000 American troops would participate in the battle. But numbers alone wouldn't stop the German armor. Panthers were systematically destroying defending Sherman tanks at ranges where American guns couldn't even penetrate. The tactical equation was brutal. Every Panther required multiple Allied tanks to eliminate it. The exchange ratio favored Germany despite their numerical inferiority. At current attrition rates, German armor would reach the Meuse River, possibly Antwerp, before Allied reinforcements could establish effective defensive lines. Eisenhower's staff presented options. All involved accepting heavy casualties. Conventional artillery was marginally effective. Panthers could advance through standard time-fused bombardments by buttoning hatches and relying on thick armor. Ground bursts expended most energy into the earth. Only direct hits on thin side or rear armor were lethal. Then someone mentioned the VT fuse. The Pentagon had forbidden ground use for 2 years. The risk of German recovery and reverse engineering was considered unacceptable. But that calculation had been made assuming normal defensive operations. The Ardennes was different. This was existential. If the German offensive succeeded, the entire European campaign could collapse. December 19, 1944. Eisenhower formally requested authorization to deploy proximity fuses on European soil. The Pentagon relented within 24 hours. 200,000 VT-fused artillery shells, codenamed POSIT, were already stockpiled in Europe, shipped months earlier in anticipation of eventual approval. Artillery units received urgent orders. Break out the special ammunition. Set fuses for air burst. Height of burst, 30 to 40 feet depending on caliber. Fire direction centers revised their entire tactical doctrine overnight. Every fire mission against German armor now defaulted to proximity fuses. The mathematics were simple. A 30-foot air burst over a Panther had 90% probability of inflicting catastrophic damage. The 16mm roof armor couldn't stop supersonic shrapnel fragments falling from directly above. By December 21st, American artillery batteries were implementing the new doctrine across the entire Ardennes front. The Germans were about to discover that their finest tank had a fatal flaw no amount of frontal armor could protect. The age of the invincible Panther was ending. December 23, 1944. 06:45 hours. Outside Bastogne, Belgium. Hauptmann Klaus Weber commanded his Panther from the turret cupola. 23 years old, Eastern Front veteran, survivor of Kursk. He'd watched Soviet T-34s explode at 2,000-meter ranges. The KWK-42 gun could penetrate any Allied tank currently fielded. His Glacis armor had deflected dozens of hits without penetration. This morning's mission: advance as part of Kampfgruppe Müller, relieve pressure on units assaulting Bastogne's perimeter. Intelligence reported American positions held only by airborne infantry. lightly armed, no armor support. Should be straightforward. The Panther's Maybach HL-230 engine rumbled as Weber's driver guided them through frozen forest trails. Visibility, 200 meters in morning fog. Radio chatter indicated friendly forces were engaging American defensive positions ahead. Then the whispering began. Not the typical whistle of incoming artillery, something different, higher pitched, multiple shells simultaneously. Weber ordered hatches buttoned, standard procedure during bombardment. The crew sealed themselves inside the steel box. The first airburst detonated 40 feet above and 30 meters ahead. The sound was wrong. Not the thunderous ground impact Weber knew from years of combat. Instead, a sharp crack, like a massive whip snapping, then hammering, metallic hail against the Panther's roof. Weber's ears rang from the concussion transmitted through the hull. "Damage report," he shouted over the intercom. "Driver reports no penetration," replied the radio operator. "Hull intact." More airbursts. Closer. The hammering intensified. Weber heard something he'd never experienced. Fragments punching through steel. The thin roof plate above the driver's compartment was failing. He heard the radio operator scream, "Reverse! Now!" The driver threw the transmission into reverse. The Panther lurched backward 45 tons of steel and 5 terrified men. Another airburst detonated directly overhead. The hammering became deafening. Weber felt hot pain in his left shoulder. Something had penetrated the turret roof, ricocheted, caught him. His loader collapsed. The gunner was shouting, but Weber couldn't hear through the ringing. Blood was running down the turret basket. The driver wasn't responding to commands. Weber tried to issue orders, but his voice sounded distant underwater. The world tilted. He grabbed for handholds as the Panther slewed sideways, tracks churning frozen mud. The engine was still running, but nobody was steering. Another airburst, more fragments hammering. The gunner slumped forward. Weber's vision was narrowing, darkness creeping in from the edges. He could hear his own breathing, ragged and wet. Something warm was soaking through his uniform. The Panther coasted to a halt, engine idling. Tracks stopped moving. Inside the crew compartment, 5 men lay still. The exterior armor was pristine, not a single penetration on the glacis or sides. Just dozens of fragment holes punched through the roof, each one precisely sized to admit supersonic steel. American infantry would find the Panther that afternoon, intact, undamaged from the front. Crew dead inside from wounds that had nothing to do with the legendary Glacis armor. The tank that couldn't be killed frontally had been murdered from above. Johns Hopkins Applied Physics Laboratory. Technical specifications. December 1944. The VT fuse Mark 53, measured 5 inches long, weighed 5 pounds, contained 130 discrete electronic components in a package designed to survive hell. The physics were elegant in their brutality. At the moment of firing, a 105mm howitzer generated peak chamber pressure of 42,000 pounds per square inch. The shell, and its fuse, experienced acceleration exceeding 20,000 times gravity. For context, fighter pilots black out at 9 Gs. Tank crews experience perhaps 3 Gs during violent maneuvers. The VT fuse endured 20,000 for 0.02 seconds. Every component was engineered for this specific violence. 4 miniature vacuum tubes formed the circuit heart. Sub-miniature pentodes originally designed for hearing aids, now shock-hardened with planar electrodes embedded in phenolic resin. The tubes were potted in wax, surrounded by oil dampening, mounted on springs that absorbed impact without breaking solder joints. The battery used reserve activation, electrolytes separated from plates until firing. The massive acceleration forced electrolyte contact, generating power. Activation time, 30 milliseconds. Just enough delay for the shell to clear the gun barrel before the circuit went live. Setback switches required both linear acceleration and centrifugal force from barrel rifling before arming. You could drop a VT fuse from an airplane. It wouldn't detonate. You could hit it with a hammer. Nothing. Only the specific combination of gun forces armed the device. The radio oscillator transmitted at frequencies between 45 and 90 megahertz, using the shell casing itself as antenna. Transmitted power, approximately 2 watts. Range, 200 feet maximum. This was deliberately short range to prevent mutual interference between shells in the same salvo. The Doppler detection principle was mathematically precise. When approaching a reflective surface, the frequency of reflected radio waves shifted proportionally to closure velocity. The fuse amplified this frequency difference. When the differential matched predetermined parameters, corresponding to optimal burst height, a thyrotron tube triggered. For ground burst applications, optimal height varied by caliber. 105 mm howitzers, 30 feet. 155 mm, 40 feet. 240 mm, 70 feet. These heights were determined through extensive testing, detonating shells above wooden boards and measuring shrapnel distribution patterns. The fragmentation physics against the Panther's roof armor were unforgiving. A 105 mm high explosive shell contained approximately 4 pounds of composition B explosive. Detonation at 30 feet altitude produced approximately 2,000 fragments ranging from 1 gram to 50 grams each. Initial velocity, 2,500 feet per second. Supersonic. The fragments formed a cone pattern approximately 80 feet diameter at ground level. Within this cone, fragment density averaged 15 per square meter. The Panther's roof measured approximately 12 square meters of horizontal surface. Expected fragment hits per airburst 100. The 16 mm roof armor could theoretically stop fragments if they'd traveled sufficient distance to decelerate. But from 30 feet, impact angle was nearly perpendicular, 90 degrees. No deflection, pure penetration mechanics. Armor penetration probability for fragments in the direct cone beneath the burst, 87%. Multiple fragments would penetrate any Panther in the kill zone. Once inside the crew compartment, fragments ricocheted between steel surfaces, floor, walls, ammunition racks, creating a blender effect. Crew survival probability, effectively 0. The Panther's Glacis armor was irrelevant. The mathematics simply bypassed it. Obergefreiter Franz Hartmann, Panzer Regiment 16. Interview. POW Camp 186, February 1945. You couldn't hide from it. That's what broke us. Not the cold, not the fuel shortages, not even the American fighter bombers. It was the artillery that exploded in the air without warning. We'd survived Russian artillery for 2 years. You learn the sounds, the whistle, the impact. You count seconds between flash and sound, estimate distance. You know when to button up, when to dismount, and take cover. We had procedures, doctrine, ways to survive. This was different. The shells didn't hit the ground, they just cracked. Overhead. 30 meters up, maybe 40. Sharp sounds like someone breaking massive icicles. Then the rain would start. Metal rain. You'd hear it hammering the Panther's roof, the engine deck, the turret. At first we thought it was air bursting by accident. Defective fuses detonating early. But it was too consistent. Every shell. Perfect height. We realized the Americans had developed something new. December 23rd, my Panther took 3 airbursts in 5 minutes. I was commanding from the cupola. Stupid, I know, but visibility was terrible in the fog. The first burst caught me exposed. I felt fragments hit my coat, my helmet. One went through my left hand. I dropped into the turret, sealed the hatch, ordered the driver to reverse into tree line cover. The second burst came while we were moving. I heard the fragments punching through the roof above the driver's compartment. The radio operator started screaming. The driver stopped responding. I tried to climb forward to check on them. That's when the third burst hit. Something came through the turret roof, ricocheted off the gun breech, took off the loader's jaw. He was gurgling, drowning in his own blood. The gunner was hit in both legs. I couldn't hear anymore. My eardrums had ruptured from the overpressure. We abandoned the Panther. Left the driver and radio operator inside. They were already dead. The 3 of us who could still move crawled 200 meters through snow before American infantry found us. Here's what you need to understand. We feared your Sherman tanks in close terrain. We respected your fighter bombers when weather was clear. But the airburst artillery? That created actual panic. By Christmas, crews were refusing to advance when your artillery started firing. NCOs had to threaten summary execution to keep some units moving. It wasn't cowardice. These were veterans who'd fought at Kursk, survived the retreat from Ukraine. But this weapon removed every defensive advantage we had. Our armor meant nothing. Our training meant nothing. The Panther's gun could kill your tanks at 2,000 meters, but what good is that when your artillery is detonating shells inside our crew compartments from 5 kilometers away? Some crews started operating with hatches open even during bombardment. Better to risk fragments than be trapped inside when the roof failed. Others tried parking under dense trees, hoping branches would detonate shells early. Nothing worked consistently. The psychological effect was worse than the actual casualties. You felt helpless, completely exposed despite sitting in 45 tons of steel. That's what broke the counteroffensive. Not your tanks, your artillery. Hartmann died from infected wounds on March 3, 1945. He was 19 years old. Wehrmacht High Command. Intelligence Assessment Report. December 27, 1944. American artillery has deployed a new type of ammunition, demonstrating unprecedented effectiveness against armored vehicles. Shells consistently detonate at altitude approximately 30 to 40 meters above ground level, regardless of terrain, weather conditions, or visibility. Initial hypothesis: acoustic sensing triggered by vehicle engine noise. Testing indicates this is incorrect. Shells detonate at consistent altitude over both active and disabled vehicles, also over empty terrain during ranging shots. Second hypothesis: barometric sensing. Also rejected. Burst altitude remains constant across varying weather pressures and elevations. Current assessment: unknown mechanism, possibly magnetic or electromagnetic detection. Recommend immediate recovery of unexploded shells for technical analysis. December 25, 1944. Near Bastogne. German forces overran an American ammunition depot during a local counterattack. Among captured materiel, approximately 20,000 VT proximity fuses still in their shipping containers. Wehrmacht ordnance specialists were ordered to Berlin immediately with samples for analysis. December 29, 1944. Heereswaffenamt testing facility, Berlin. 6 senior engineers examined the fuses under laboratory conditions. They discovered the vacuum tubes, the battery assembly, the circuit components. What they couldn't comprehend was how these delicate parts survived artillery firing. Chief Engineer Dr. Wilhelm Renz wrote in his report, "The American fuse contains 4 vacuum tubes of advanced miniature design. However, such tubes cannot possibly function after experiencing gun acceleration forces exceeding 15,000 times gravity. The glass envelopes would shatter. The filaments would break. The solder joints would fail. We conclude these are defective units or decoys intended to mislead our technical intelligence. The Americans must be using a different mechanism, perhaps magnetic induction or capacitive sensing, and including false vacuum tube components to obscure the actual operating principle. Recommend continued analysis but assign low priority. The fuses as presented are technically impossible. The German engineers never tested the captured fuses electrically. They assumed malfunction based on theoretical analysis. This error would prove catastrophic. Meanwhile, American intelligence learned of the capture within 48 hours through intercepted German communications. Wright Field in Ohio received emergency tasking. Develop countermeasures, assuming the Germans would eventually determine the VT fuse's operating principle. Within 2 weeks, engineers created electromagnetic jamming equipment, 200 units designed to disrupt VT fuse radio frequencies. The jammers were rushed to England for installation in bombers, intended to protect aircraft if Germans deployed reverse-engineered proximity fuse against Allied air formations. The jammers were never needed. The Germans never activated them. But German tactical doctrine changed radically in January 1945. New orders for Panzer units: avoid open terrain when American artillery is within range. Seek covered positions, buildings, dense forest, terrain depressions. Deploy vehicles individually rather than in formation to minimize casualties from single airburst. The problem was obvious to every tank commander. These orders negated the Panther's primary advantages. Long-range firepower was useless when hiding in buildings. Formation tactics were impossible when dispersing individually. The KWK-42 gun that could engage targets at 2 kilometers became irrelevant in close terrain. Armor doctrine developed over 4 years of combat had been rendered obsolete by a $20 electronic device. Panthers designed to dominate open battlefields were now relegated to defensive positions that nullified their capabilities. The tactical revolution was complete. The age of armor supremacy was ending, and the war had 3 months remaining. January 25, 1945. The Battle of the Bulge officially ended. The numbers told a story that would reshape armored warfare for generations. American artillery fired 1,255,000 rounds supporting the battle. 4,155 guns participated. Approximately 15% used VT fuses. Roughly 188,000 proximity-fused shells detonated over the Ardennes. German casualties: 100,000 killed, wounded, or captured. Tank losses: 320 Panthers destroyed or abandoned. For context, German factories at peak production manufactured 250 Panthers monthly. The Bulge consumed more than a month's total output in 6 weeks. But the strategic impact transcended mere statistics. General George Patton wrote in his diary, "The funny fuse won the Battle of the Bulge for us. I think that when all armies get this shell, we will have to devise some new method of warfare." He was correct. The proximity fuse had demonstrated that armor design philosophy, maximizing frontal protection while accepting thin roof armor, was obsolete. Post-war tank development reflected this lesson immediately. The Soviet T-54, introduced in 1947, featured 30 millimeters of roof armor, nearly double the Panther's protection. The American M48 Patton incorporated composite roof armor and spaced plating. The British Centurion used similar principles. Modern main battle tanks like the M1 Abrams mount sophisticated defenses against airburst threats. Reactive armor tiles that detonate outward to disrupt incoming fragments. Active protection systems that intercept projectiles before impact. Composite roof armor designed to fragment and ablate under airburst attack. The technological race initiated by the VT fuse continues today with programmable airburst munitions that can adjust burst height in real time, drone-delivered explosives optimized for top attack profiles, and loitering munitions that select optimal detonation points based on target geometry. The fundamental principle remains unchanged 79 years later. Why attempt to penetrate thick frontal armor when you can bypass it from above? The VT proximity fuse program cost $1 billion in 1940s currency, approximately $15 billion modern dollars. Over 22 million fuses were produced. Each contained miniaturized electronics that wouldn't become commonplace in consumer devices for another 30 years. The fuse was classified at the same level as the Manhattan Project throughout the war. Fewer than 100 people knew its true operating principle. Japanese and German recipients of proximity-fused fire never understood what was killing them with such precision. Secretary of the Navy James Forrestal stated, "The proximity fuse has helped blaze the trail to Japan. Without the protection this device gave the surface fleet, our westward push could not have been so swift and the cost would have been immeasurably greater." Winston Churchill wrote, "These proximity fuses proved potent against the small unmanned aircraft with which we were assailed in 1944. The Allied victory in World War II resulted from numerous factors: industrial capacity, intelligence capabilities, strategic leadership. But among the technological contributions, 3 stand paramount: radar, the atomic bomb, and the proximity fuse. One of these cost $18 per unit by 1945, and completely ignored the Panther's Glacis armor. Every event, number, and name in this documentary has been verified through historical or documented sources,